Welcome to a video on section 4.3, the bottom of page 4 to page 6. So let's start with interpreting graphs, example 4, which is the bottom of page 4 of the 4.3 notes. So the following graph shows the position function of a particle moving in a straight line at approximately what time is the particle's velocity equal to 0 and acceleration equal to 0. So here we're coming back to linear motion. Now remember, if you have the position function, velocity is simply the derivative of the position function, and acceleration is the derivative of the velocity function. Or you could think of it as a second derivative of the position function. And now that we know that second derivatives are, or when your second derivative is positive, it's concave up. When your second derivative is negative, it's concave down. We can now utilize that to help us answer these two questions here. Well, if velocity equals 0, I think that should be pretty easy. That's when we have horizontal tangent lines, right? Because that's when the derivative is 0. And it looks like that happens, you're going to have to kind of estimate a little bit, like a little bit less than 1, so maybe at 0.7. And it looks like a little, somewhere between 2 and 3, so maybe 2.5. And then something a little bit higher than 4, like maybe 4.2 or 4.3. So at 0.7 seconds, and actually there was no units for time labeled here, but that's okay. But 0.7, 2.5, 4.3 is when our velocity is 0. Now this gets a little tricky about the acceleration. So remember, concave up, you have a positive second derivative, concave down, you have a negative second derivative. But we want the acceleration to be 0, so we want to see when the second derivative would be 0. And that usually will happen, not all the time. So let me actually rephrase that. When you have a point of inflection, it's possible, or sorry, when we have a second derivative that's 0, it's possible to have a point of inflection there. But definitely if you have a point of inflection, for sure, your acceleration, or your acceleration could be 0 in this case. So let's see where it could be concave up. Probably looks like it's concave up in this region, concave down over here, concave up over there. So concave up over here and over here, concave down over there. So it seems that our points of inflection would probably happen right there and right there. So if we were to kind of ballpark or guess where acceleration could be 0, I'd probably say about 1.5 and maybe about 3.5. Also, another way of looking at it too is when the value of the derivative or the slopes of the tangent lines are increasing, that's definitely going to be concave up, but then when it starts decreasing is when it's concave down. And it probably would happen right around here, where all of a sudden it seems like the value of the derivative or the slopes of the tangent lines will start decreasing, where here it's positive and there it's also positive, but you start noticing a change there. And likewise over here. Okay, let's move on to something new, something called the second derivative test. We've learned about the first derivative test, and what that enabled us to do was to take our critical points and determine if our critical points represent a maximum or neither. And it was very simple. We took the first derivative, we found the critical points, we made a sign chart, we looked at each interval whether the derivative was positive or negative, so we could see whether the function is increasing or decreasing. And if it was changed from increasing to decreasing, the first derivative, then we knew we had a max, local max. And if it was going from negative to positive, we had a local min. So another test we could do is a second derivative test. And let me show you how that works. So say we have the following situation. F of 2 is 1. And we're also told that f prime 2 equals 0. So we have a horizontal tangent, but that still doesn't tell us enough, because what if it's like this, or what if it's like this? So we still don't have enough information. Oh, but we have that. That's concave down. So I like the second way. I like to have the graph look like have a frowny face, right? That looks pretty good to me. And we still have horizontal tangents, so everything's all good here. So what does this tell us? That we probably have a local max at x equals 2. Or a local max of 1, probably be more proper, at x equals 2. So what we can deduce, oh, and by the way, no, never mind, I was thinking of something else. So what that tells us is this theorem right here, which is basically going to be the second derivative test. If your derivative is 0 at a certain x value, and the second derivative has to be negative for that same x value, then we're going to have a local max at x equals c. Where, again, if we have a first derivative of 0 at a certain x value, but this second derivative is positive, then we have a local min at x equals c. Now, what if your second derivative was not positive or negative? What if it was 0 or did not exist? Then, of course, just use the first derivative test. So let's try this new test on this function here. F of x equals 2x cubed minus 3x squared minus 12x. So the first derivative should be pretty easy. 6x squared minus 6x minus 12. Second derivative is also pretty easy. 12x minus 6. Okay. Now, if we see where the derivative could be 0, because that's important. 0 equals, and we factor out 6, x squared minus x minus 2. 0 equals 6, x minus 2, x plus 1. X equals 2 or negative 1. So that's where the derivative would be 0. Now let's actually see the value of the second derivative. F of 2 is going to be 18. Sorry, f double prime 2 is 18. F double prime negative 1 is going to be negative 18. Oh, okay. So we have a positive second derivative. So that's going to be concave up. Negative second derivative for negative 1, that's going to be concave down. So if I imagine how this would look, you know, at x equals 2, which actually I don't need to calculate where it is exactly. But the bottom line is we'd probably expect something that's concave up at x equals 2, and you know, since 0 is 0, we're going to have a minimum there. And then of course we have this at negative 1, where it's concave down, and again we have a horizontal tangent. So what this means is that we're going to have a local max at x equals negative 1, and a local min at x equals 2. And that's because, again, our second derivative at x equals 1 was negative, making it concave down, but because we had a derivative of 0 there, that makes it a max. And for x equals 2, we have something that's concave up with the first derivative that was 0. Of course, that made it concave. That was concave up, that makes it a min. So no sign charts necessary here. If you don't like sign charts, maybe you could try the second derivative test. So no sign chart is necessary. And then, you know, the proper language, you say f has local maximum of b at x equals a because your second derivative is less than 0 at x equals a, or because it has a minimum value of x equals c because second derivative was greater than 0 at x equals c. If you're using the second derivative test, that would be the more proper way. So I know it seems a bit counterintuitive to say your second derivative is positive, a minimum value, but again, it's concave up, right? And so that's what's happening there, where the other way it's concave down. Okay, let's look at page 6. And we'll do one of these examples here, and then we'll end the video. And then we'll do example 8 together as a class. Actually, sorry, example 6 and 7. So here we're going to use the derivative graph to graph f. So use the following graph of y equals f prime x, estimate the intervals in which a function f is increasing, decreasing, also estimate the x-coordinates of all local extreme values. Okay, well, the thing is that when your derivative is positive, you have an increasing function. When your derivative is negative, you got yourself a decreasing function. And of course, local extreme values could happen. You got to be careful. But if f prime equals 0 and f prime goes from positive to negative, that's a local max. If your f prime is 0 and f prime changes from negative to positive, you're going to have yourself a local min. And in addition to that, if f prime does not exist, that could also happen too. But we see that not happening here because it looks like all the f prime values exist for this graph here. So clearly, this is an f prime graph. So we want to look at the y values. Clearly, the y values up to -3 and past 3 are increasing. So for part A, it's going to be from -infinity to -3, and from 3 to infinity is when we're going to be increasing. For part B, it's going to be decreasing because when it's basically negative. Now you got to be careful for this one because we do see that derivative is 0 right there, and we want the derivative to be negative. So we would say from -3 to 5, the function is definitely decreasing. I mean, yes, it is 0 at x equals 1, -3 and 3, but we'll still have that included. And then for part C, we're going to have a local max. So here it goes from positive to negative. So we have a local max at x equals -3. A local min. Oh, oops. That was 5 to infinity for part A. Sorry about that. Thought we had this graph as being symmetric. Apparently it's not symmetric. And then local max. Sorry, local min at x equals 5 because the derivative changed from negative to positive. But you're not going to have anything at x equals 1. You're not going to have a local extreme value because the derivative does not change sign. So that's what happens there. Okay, let's look at example 7. A function continues on an interval from -3 to 4. The discontinuous function f prime with domain -3 to 0, 0 to 4 is shown. Find the x-coordinates of all local extrema and points of inflection. Sketch a possible graph of f. Okay. So now in this case, our derivative does not exist. At x equals 0. And that's because it's not continuous, so it's not differentiable there either, right? We've talked about that many times where it's not differentiable, where it's not continuous, not differentiable. But we are saying that it is continuous from -3 to 4 with the 0 not included. So let's go ahead and do a sign chart. We're also going to notice that we're going to have a horizontal tangent at x equals 2 for sure. Okay, hold on a sec. So this is actually a derivative graph. Okay. So if it's a derivative graph, let's backtrack here. This is a derivative graph. Clear our derivative 0 at 1 and 3. And of course, the derivative does not exist at x equals 0 because it's discontinuous there. But the function itself is continuous. So keep that in mind. Okay. Sorry about that. I thought we had the original graph here. This is actually a derivative graph. So let's now do a sign chart. We're going to locate 0. And we do have endpoints, looks like, at -3 and 4. And we have 1 and 3. Now, if I do my sign chart, 0, 0 does not exist. And it's positive here, negative there, positive and negative. If you test all those different values, or just start from the right and work your way from the left, plus we just see it's above the x-axis. And it's below the x-axis from 1 to 3. And the derivative is also above the x-axis from 0 to 1 and below the x-axis from -3 to 0. So this is going to be a local min. This is going to be a local max. Back to being a local min. And as the derivative is increasing towards 4, that's going to be a local max for right endpoints. And derivative is decreasing from -3, that's also going to be a local max. Okay, so we have max, min, max, min, max. So now we found the x-coordinates of all local extrema. And for the points of inflection, actually that's going to be at x equals 2. That's when we're taking the derivative of the derivative, right? Point of inflection at x equals 2. That's the only place where that happens. And also you want the sign to change. So if you do a sign chart for the second derivative, if we look at 2, and again, it's not differentiable at 0, and here's our endpoints at 4 and -3. Our second derivative is definitely 0 between -3 and 0, because you're taking the slope of the derivative graph. It's negative from 0 to 2, and of course it does not exist at 0. It's the second derivative is 0 at 2. And the second derivative is definitely positive from 2 to 4, because again, you're doing the derivative of a derivative to get the second derivative. So it only changes that 2. So we have a point of inflection right there. Okay, and again, we have our local maxes, or maxima, x equals -3, 0, and, -3, 1, and 4. And local min at x equals 0 and 3. So a possible graph could look something kind of like this. We could have a point at, well, we definitely want something not differentiable at x equals 0, and definitely want the function to be decreasing. And because the second derivative is 0 there, we'll probably want something that's a bit linear or a constant slope. So say it has something kind of like that. And I have another endpoint right there. And we want a min at 0, but a max at 1. So maybe something kind of like this. And also we're showing that it's concave down from 0 to 2. And then we hit a min at 3, and then back up that way. So here I have a min, here I have a max, here I have another min, here I have another max, and here I have a max. And also it's concave down, concave up, 0, second derivative, because if you have a linear function, the derivative is a constant, and the derivative of a constant is 0. So when second derivative is 0, you want a linear portion of the curve for the original graph. And I think that So this concludes the video. We'll discuss a little more detail next time. And we'll also work on example 8 in class. And we'll wrap it up with the last page in the notes. Oh, and I forgot my prediction for the CCS open title. Actually, should have gone red here for Sacred Heart, not blue for Element. CCS Open Championship. I think it's going to be a very, very close, slug it out type of game. I'm going to say SHP 16, Bellarmine 14. We're going on a last-second field goal. It's going to be very dramatic. So that's my prediction. All right, see you guys later.